Nếu bây giờ nó online là được rồi, mình online view rồi.
To be honest, it has a nice screen. I don't care what I understand. It does have a nice screen.
Are you okay? Yeah. Okay. So we just discussed the second midterm. So I hope no problem. There, right? Any question? Further questions? Alright, that's good. Alright, I think we are going to discuss the new chapter. It's called magnetics, right? Electromagnetic. Everybody knows magnet, right?
Yes.
Alright, magnet. We have N, we have S. What is N? North. S is the south. Right? We have magnetic field lines, like this. The magnetic field lines outside of the magnet. It is from north to the south. Inside the magnet, it is from the south to the north. So they form a closed loop, right? So like this, closed loop. So inside from south to north, from outside from north to the south. And if we look at the lines, they have some dense area, some less dense area. In the dense area, the strength of the magnetic is strong, is large. So that means the magnetic at this area is not that strong compared to this one. And how to draw the magnetic lines, field lines? One way to visually see this is we have magnet, and then you put a glass on top of it, then you put some iron fillings on top, then you are going to see the things like the pictures on the left. Right? Or if we draw on the first slide, we draw the lines. Okay, so here this one is the Earth. Right? Which one is the north? The due north is on top, right? But the magnetic north is on the bottom. They are opposite. They do not overlap, but a little bit, very close. But on the top is the due north, but the magnetic north is on the bottom. This is the due north here. But the real due south is not overlap, but very close. So you can see from outside, the magnetic lines goes from the north, this north, magnetic north, to the south. The magnetic lines, what is it?
Just right in my brain, I ain't never heard of before.
The magnetic lines are 3D. It's not only 1D. So what we draw on the first two slides is on 2D, but you need to imagine this, right? Look at this one on the top, that is wet, right? So can you imagine this is 3D?
That can be illustrated.
So any magnetic lines are 3D. Right?
They're relatively good.
How does the magnetic field generate? How are we create a magnetic field? Anyone knows that?
In Earth, what causes it?
Anywhere, for example, the magnet, or any magnet. How do we generate this magnetic field?
Yeah, I go to Wednesday.
We have electrons, right? Electrons will rotate. If electrons rotate, then we use the right hand rule, then rotate like this way, then we follow, use both fingers, curve this, then that side is the north. So we know for any material, metals or anything here inside, we have a lot of numerous electrons. So all these electrons give us a magnetic field. Now the question is, why some material has magnet, some looks like no? What happened here? In general, the material has the electrons rotate or moves random like this. So they generate north pole, south poles also totally random. Right? So So this one is North Pole, South Pole, North Pole, South Pole. All collectively, they do not exhibit any magnetic property to outside because they just totally random orientation. But if you put this thing and a magnet, it is something like you align them together. So you can see in this situation, all the north to this way and all the south to this way. So collectively, for this big magnet, then this part is the north, this part is the south. Does it make sense? Right? So that is how magnets are generated. Okay, look at this picture here. You imagine this is a physical magnet. And we know this is the north, this is the south. Question is, if I cut in the middle, what happened to the left-hand side? We have a north, what is in the middle?
South.
South? Or nothing?
Nothing.
Nothing?
South. Yeah.
So we cut from here, right? So this part is north, this part is the south. If I cut from the middle, consider only this part. This is again still north, right? And what is this part?
South.
South?
Yeah.
How about I cut from here? This is north, what's this part?
South.
Still south, right? So you just imagine like this one. Even you cut this one, this is north, this is the south. Right? But if you have a lot put together, north, south, so this two looks like they can cancel. Kind of sense, right? So overall, this part is a strong north, this part is a strong south. But if you cut any, they still have south and north. So that means there's no such thing as a monopole. You cannot have only one. You said, okay, this magnet has only north pole, no south pole. Okay, there's no way you can do this. Why there's no way you can do this? Because it is generated from the rotation of the electrons. The electron rotate along an orbit. You always have, use your right hand, on the top that's north, on the bottom that's the south. You always have these two poles. So you cannot separate. Alright, so this is the magnetic material and magnetic quantities. We know this magnetic lines we call the magnetic flux. And the unit for magnetic flux is called the Weber. The unit of flux density, that means the flux per unit area. Then obviously it is a Weber per square meter. We use a standard unit. That's flux density. The unit for the flux is Weber. The flux density is Weber per square meter. And also, that is called Tesla. So we represent by T. And Tesla is very large unit. Sometimes we do not use this. Instead, we use a smaller unit, which is called a Gauss. Here. 1 Tesla equals 10,000 Gauss. Right? Go back here. This is how we calculate the magnetic flux. The magnetic flux is B. The B is magnetic flux density, and the phi is the magnetic flux. Then we divide it by the area, give us the magnetic flux. Keep in mind, you need to use the right unit. So the magnetic flux density equals the flux divided by the area. And that gives us the unit of Tesla. And as we said, Tesla is very big. Most probably we are going to use a smaller one, it's called Gauss. And the relationship between these two is 1 Tesla equals 10,000 Gauss. And this is the meter, it's called Gauss meter, used to measure the magnetic flux density. Alright, so here we have an example. What is the flux density in a rectangle core that is 8 millimeter by 5 millimeter? Is flux equals 20 micrometer.
Can you get back to the formula real quick? I missed part of it right there.
This one.
Yeah, okay.
The flux density B equals the flux phi divided by the area A.
Okay, thank you, sir.
Right? And we have an example here. Right? The flux is 20 microwave, and the area is rectangle. Length equals 8 millimeter, the width equals 5 millimeter. What is the flux density? 0.5. Oh, you're quick. Okay. Anyone get the result? What is it? 0.5. Oh yes, very fast. Right? How we do this? Use 20 micro divided by the area. The area is 8, 10 times negative 3. And then times 5 times 10 to the negative 3. That will be 40 times 10 to the negative 6, which is 40 micro. Right? Then on the top is 20 micro over 40 micro equals 0.5. 0.5 what?
Micro. Something.
Something. What's it?
Micro Teslas.
Okay. Micro Tesla? The micro with cancel with the 10 to the negative 6 on the bottom. So it is a 0.5 Tesla.
Yeah.
That unit is very, very large. Okay, we want to convert it into a Gauss. How many Gauss is that?
100,000.
5,000, right? Because each Tesla equals 10,000. So 0.5 equals 5,000 Tesla. Okay, so 5,000 Gauss. Right? What you do is write B equals P over A. You need to do like this, right? I do not only give me the numbers except in the multiple choice. So write the formula, plug into numbers, and give me the result. It's 0.5 Tesla, and which equals 5,000 Gauss. Okay. The next example is magnetic flux lines surround a current carrying wire. What does that mean? That means, for example, this is a straight wire, straight or not. Usually, when we demonstrate this is straight. So the current, we have a current passing through this. How to implement this in labs? What we do is we have a battery here, then we have just this wire. And this is the wire. We make this a little bit larger to show that there's a cross section for this. You do not do this. Can you do this in the lab? Maybe. Maybe. Can you do this? Why cannot?
It's a hazard.
It's a hazard. So why? I show you here, but I do not suggest you to do this in the lab. Just like this.
Don't blow up.
Okay, yes. This one is short, right? This is straight wire. You connect directly to the positive and negative terminals of your battery, then which part will be very hot?
The one on the right.
Battery will be very hot, right?
That's what I meant to say.
And so that's very dangerous. Instead, we are going to use, for example, this is current source. That means the current is fixed. For example, this A equals, instead I use just the current source like this. So the current equals, for example, 10 A. This one is good because the current is fixed. If we have a current go this way, and let's make the current go up. Doesn't matter, right? Go up, so the current will go up. We have current here. So what happened to this wire? This wire is called a current carrying straight wire. Then there will be magnetic field surrounding this. What is the direction of the magnetic field? You use your right hand rule. The thumb direct to the direction of the current, like this. Then you curl your 4 other fingers. That fingers give us the direction of the magnetic field. So can you imagine this? Up, then like this. So the magnetic flux line, magnetic field lines will be go like this. Does that make sense? Little bit? Can you imagine the magnetic flux? You use your thumb, goes up. in the direction of the current flow. Then the other four fingers curved, it is in the direction of the magnetic field line. Okay? Everybody, can you try? So that means on the right hand side, if we only consider on the two-dimensional, on this whiteboard, on the right hand side, the magnetic flux line will go inside or outside?
Inside.
Inside, right? Perpendicular to the board, but go inside. So we draw that with a cross. How about on the left hand side? What's the direction for the magnetic flux on the left hand side on the board?
It goes out.
Go outside, right? So we are going to draw this with a dot, right? Like this. This looks like the arrow, right? You are looking into the arrow. This one looking along the arrow. So this you only see the back. This one you see the front. So this is how we represent the direction of the magnetic flux. You are going to see this, learn this a lot in physics 202, electromagnetics later. But this one give you a brief introduction. Okay, any questions? And again, imagine this, all these magnetic are three-dimensional. For example, if you look from the top to the bottom, what does it look like? What shape is the magnetic line? If you look from top to the bottom,
It's so circle.
it's a circle, right? Yes?
Yeah.
You can imagine, right? If you go look from top to the bottom like this, it will be the circle. Right? Okay, that's good. The field lines are concentric circles. You already know that. As in the case of a bar magnet, the effect of the electric current can be visualized with the iron filings around the wire. The current must be large to see this effect. If the current is small, then it's not that obvious. If the current is large, you need to be careful. So when you do this exam, if you want to demo this, be careful. Right? Think before you do this. Another property is called permeability, represented by mu. That defines the ease with which a magnetic field can be established in a given material. If the material can easily establish a magnetic field, then this mu will be very large. If it's not easy, then this mu will be small. So that quantifies how easy it to create a magnetic field. It is measured in the unit of wave per ampere turn meter. That unit is very lengthy. Right? Can you write out the unit for this? Can you write out this by read of this text? Wave per ampere turn meter. Right? So the unit will be wave like this. Ampere is A. Turn, how many turns of the coil? That is unitless, right? So you don't need to write anything. And then there's the length. The length is a meter, right? So like this. This is the unit.
So that's
Wave per ampere turn and meter. The length, per length. The permeability of a vacuum mu equals 4 pi times 10 to the negative 7 wave per ampere 10 meter. That number is very small. But this number is used as a reference. So that's why mu sub 0, sub naught over there. So that means that's the reference. That is the permeability for free space for vacuum. The relative permeability, mu with a subscript r, is relative, is the ratio of the absolute permeability to the permeability of the free space. For example, if a material has a permeability, the mu equals 2 pi, let's see this, that's 10 pi times 10 to the negative 7, right? Suppose you get the material, the mu equals this. What is the mu r? What is this? That is the relative permeability of this with reference to the permeability of a free space, which is the mu 0 equals 4 pi times 10 to the negative 7, right? So what is this is the free space. This is your material. Then what is the mu r? What is it? It is this one divided by this, right? 0. This is 10.
10 over 4.
10 over 4. So that equals 10 over 4, so equals 2.5. So the relative permeability equals 2.5. Right? So later time we are going to write the mu here equals 2.5 mu sub naught. Like this. Right? Or in general, mu equals mu r times mu sub 0. Usually we do not give this one in absolute value. We just use the relative, mu r times mu sub 0. So you can see mu r equals mu divided by mu sub 0. Right? Reluctance is the opposition of the establishment of a magnetic field in the material. Does this remind you anything? The opposition of what is it? Resistance, right? Yes, that is very similar to resistance. Resistance equals voltage divided by current. It is the opposition to establish a current. So reluctance is the opposition to establish a magnetic field. So R equals L over mu times A. L is the length of the material. A is the area of the cross section. Right? If you have a material like this, the magnetic field, suppose this is the material, right? The magnetic field is supposed to go from this way to this side, this way. Then L is this length. Right? And A is this cross section. Right? Just like in the resistance. How to calculate the resistance? The resistance equals the resistance equals, still remember how to calculate the resistance? Equals resistivity times the length divided by the area of the cross section. Right? Suppose if we have something like this, or we draw a circular, right? Like this. And what is the resistance of this resistor? And there's a cross section here that is A, this length equals L, and this material has a resistivity of rho. Then the R, resistance equals the rho times the length, then divided by the area of the cross section. We know this before, right? And this one is the same thing. Reluctance, right, equals L over mu times A. So you can see this mu is very similar to 1 over rho, resistivity. Recall that the magnetic flux line surrounds the current carrying wire, right? We know that, right? There's a wire, and we can use the right-hand rule to determine the direction of magnetic. But if you have a coil, that means a multiple of wires, then the magnetic flux field density will be much stronger. Right? If the number of turns is equals 10, then it will be 10 times stronger. So it's proportional to the number of turns. The cause of a magnetic flux is called the magnetomotive force, MMF, which is related to the current and the number of turns of the coil. Let's do, for example, here. As we said, if we have this straight wire, we know the magnetic field will be inside, so the current goes this way, then outside like this, right? How about if we have a coil only one turn? So the current will go, for example, this way. What is the direction of the magnetic field? Okay? You can think of like this one as straight as here. Then you go this, so this one will be outside, right? Inside, and this one will go outside, right? And this same thing, so all inside will be this, and the outside will be like this. If you do part by part, fraction by fraction. Or better way is you just use your right hand, curve your four fingers in the direction of the current, because this is a coil, right? Then the thumb gives us the direction of the north. Right? So you do this, then this one means the magnetic flux line will go outside. Does it make sense? So like this, right? And this one has only one turn. If the coil has multiple turns, like this, how to draw a coil? And like this, not good, right? The current goes out like this. Then we know the north is this side, right? And we have, instead of we have only one turn, we have multiple turns. Then this magnet will be stronger than this by a fraction, by a multiple of this one, 1, 2, 3. So this one N, this is north, right? And the number of turns equals, for example, 3 in this case compared to this one. Then the magnetic field will be 3 times stronger than this one. So that's why if you look at your radio or something, there are a lot of coils, even motors, generators, there are a lot of coils. It gives us a much stronger magnetic field. Okay. So the magneto MMF is calculated by N times I. N is the number of turns, I is the current. And the unit for MMF is A turn. And turn is just write the turn. Right? Turn actually has no unit. N is the number of turns of the wire in the coil, and E is the current. We said reluctance is very similar to resistance. Resistance corresponding to our Ohm's law. And for magnetic field, we also have a similar Ohm's law, called Ohm's law for magnetic circuit. This one? Right? The magnetomotive force equals N times I. So the Ohm's law for magnetic circuit is phi equals Fm divided by reluctance. So what is F? The force. It's similar to the Ohm's law for electric circuit. F is similar to the voltage, right? And the phi, magnetic flux, is similar to the electric circuit, the current. Ohm's law for electric current is, for electric circuit is I equals V over R. And for magnetic field, that is phi equals F over reluctance. We do not analyze magnetic circuit here. This is only give you an idea. So later time, when your high level circuit analysis, you are going to analyze the magnetic circuit. But here, you only know magnetic circuit is very similar to electric circuit. We have corresponding very similar concept, reluctance, resistance, MMF corresponding to voltage, and the magnetic flux is very similar to the electric current. So you only need to know, okay, there's a similarity between these two. That's all. Okay, we have problem. What flux is in a core that is wrapped with a 300 turn with a current of 100 mA if the reluctance of the core equals 1.5 times 10 to the 7. What is magnetic flux? Right? The formula is on the top. Magnetic flux equals MF divided by the reluctance. So what is FM? Okay, magnetic force equals what? Equals the current times the number of turns, right? So in this example, the current equals 0.1 A. We use the standard unit, right? So 0.1 A, which is this one. So 0.1 A, then the number of turns equals 300. So 0.1 times 300, that will be equals F, which equals 30. So 30 is on the top, right? Okay. On the bottom, that will be 1.5 times 10 to the 7. Right? All these units are standard. So we don't need to care about the standard. So 30 on the top, 1.5 times 10 to the 6, times 10 to the 7, which equals 15 times 10 to the 6, right?
Yeah.
Okay? So we use this one because over 10 to the 6 give us a micro. 1 over 10 to the 6 give us a micro, right? So on top equals 30, on the bottom is 15. So you can see that equals 2 micro. So that is the result. Does that make sense? Everybody? Equals 2 micro. Yeah. Make sense? So what we do here is on the top. That is the trick we usually do this kind of calculation. Right? On the top, then 30 over 2 over 1.5 times 10 to the 7. Right? Instead, we directly calculate this. We are going to use this as 30 on the top, 15 times 10 to the 6. Right? We know how to convert this representations, okay? Scientific representation or engineering. Right? So we know that. So in this case, right, now this one was 2 and 1 over 10 to the 6. That gives us 10 to the negative 6, and which is the unit of micro. Right? So 2 micro what?
Micro.
That is the phi, right? Phi. What is the unit for phi? Wave, right? Okay, so like this. Right? Does it make sense?
What'd you write right there? I can't see it on the screen. Okay. Micro.
Or if we 10 negative 6, this. Right? But we prefer is 2 micro. Alright, let's see if our result is correct. Right? 2.0 micron. Why use 2.0? Anyone can tell? We use just equals to 2. Why use 2.0? Which one is better? 2.0 is better. Okay, so you know 2.0. Why 2.0 is better?
It's more accurate.
More accurate. How about 2.000?
More accurate.
Even more accurate.
Even more accurate. It's necessary.
Yes.
No, not necessary.
Well, it's not.
Yes, no,
Yeah.
not necessary. Why is not necessary? Huh? Because of what?
It's already micro, right?
It's 2.
No, because the reason is the numbers given is 1.5. So we have only 2 significant digits.
Yeah.
So the result, we have only 2. We need only 2. If we have more, 2.000, that makes no sense at all. Looks like accurate, but accurate is less. nothing. So you need only 2. We use the smallest number of significant digits. In this example, 1.5, so only 2. If you use 2, that is okay, but 2.0 give us more information. Okay. Any question on this? So now in the final test, all these questions you need to think. So combine everything from the very beginning all the way to the last. The magnetomotive force is not a true force. What is the unit for a force? What's the unit for a force? Newton, right? How large is 1 Newton?
1.4 joules, 1 something.
You remember the example like the apple, right?
1 meter.
1 apple, okay, 1 apple is like 1 Newton. Right? You raise your apple to 1 meter high, that is like 1 joule energy. Alright, so good, you remember this. But MMF is not a real force, so the unit is not Newton. Instead, what is the unit for this? What is the unit for MMF? Remember how to calculate this? FM, how to calculate this? Because N times I, right? I is A, N is a turn, so this is A times turn, right? So it's not Newton. But can be thought of as the cause of a flux in the coil or other material. Look at this. The current is in the coil, cause the flux in the iron core. Right? So here, suppose we apply current. Suppose the current goes this way, then use the right hand. So suppose the current goes all this way, like this. Here, so on the top that is north.
Oh, that's
Right? Okay, so this north, then the magnetic flux will be guided through this material, ferromagnetic material. There will be some leak outside, but most of them will be inside this one, just like the current. If you have current, most of the current will be in most of the energy will be in the wire. But there are some other energies will be outside. Do you believe me?
yeah.
Can you give me an example that the current, most of the energy is inside, but some energy will be outside? Sparks. Okay, that is, that is. How about there's no sparks? Just you see nothing, just the current flowing through this.
Filings.
What is your question?
Wireless. Okay, so here I said the magnetic field, most of them will be inside this material, right? But I said some part will leak outside. That means, for example, if this is a large transformer, like the power transformer, if you go close to it, then if you have some meter, you may feel the magnetic field. So there's some leakage outside.
Energy lost to heat.
Okay, energy.
It's just enough energy.
This one is very similar to, for example, electric current. We know the electric current can flow through the wire, right?
Yeah.
So the most of the energy will be in the wire, like here. How about the outside of the wire? Do we have any leakage or something?
Yes.
That is called radiation, right?
Radiation.
You have a cell phone. Your cell phone will receive the energy from outside. Your antenna just like this. Definitely you do not connect this one to any source. But this one will collect the energy. Where does the energy come from? From the air. So this radiation leakage is called radiation. Very similar to this. Okay? And you are going to learn a lot of new things later time. So what is the MFM for 250 turns which has a 3A? What is it? So equals 750, right? Okay, so 750A dash T turn. Alright, that is the Hall effect. That is very, very famous and very, very useful. Right? You may already have this. You have a smartphone, right? Right? You may have a Fitbit or something like that. They have some device inside. They may measure the magnetic field. And that device is called the Hall effect. Right? So like this one. What does this mean? Right? Suppose we have a north pole, south pole, magnetic field. So the magnetic field will go from north to south, right? Like these arrows. Now we have a conductor like this, and the conductor is carrying a current. The current goes from top to the bottom. Is this clear? So that is the setup. Then what will happen? This side close to you, and that side inside the board. Between these two sides, we are going to have a electric voltage. That is called the Hall voltage. Yeah? Anyone knows how this happens? Right? First, let's repeat. You have magnetic field like this, north, okay, or this way, and you have something like this here, up, and we have a current goes down. Okay? Then this one is three-dimensional, right? Okay, so the edge closer to you will have some positive charge, and the edge further away from you, that blue part, will have a negative, or more specific, electrons. So that means if you connect this positive with this negative, then you are going to see there's voltage. And if you close this, there will be a current. It's called Hall current or Hall voltage here. So what happened here?
Is that like wireless charging? You talking about like wireless charging? Is that what this is?
Wireless charging, not exactly wireless. Wireless charging will be discussed later times.
Wireless charging is like a
That's not wireless charging.
modified Tesla coil.
Everybody explains a lot of things.
I-
What is that?
If you know what a Tesla coil is, you would know.
I don't know what that, I'm talking about.
Okay, so now I may have a video for you to see this. I don't know if I can let's see. So this will work.
Just look at a picture of Nikola Tesla smile and you'll understand everything.
Oh, sorry.
What is that? They're like, oh, I invented that. That's my invention. You made this? You made this? Yeah, what?
Why? I don't know why we cannot play here. I played it last night on my computer.
Is the video you're trying to play, is
Not
it
available in your country.
on YouTube or is
Oh,
it?
there. Okay, here's the. There are a lot of YouTube videos discuss or images discuss about this Hall effect, but a lot of them are incorrect.
Oh.
Alright, so you need to be very careful.
Can we get it again?
I don't know why. Cannot. You can download this from my website, then you can. Yeah.
Could I thank it?
Okay, let me just explain with the diagram. Right? There is a Lorentz force. That means any charge carrying item moving in a magnetic field will suffer a force. That is the real force. Okay, it's called the Lorentz force. That force will be calculated by the Q, which is the electric charge, then times V cross B. Right? This is has direction, the movement, the velocity. This is the magnetic field here. Right? So this gives us the strength and also the direction. Suppose we have like this, and let me see, the magnetic field. Right? I just use the one we discussed here. Right? Like this. Is it three-dimensional? Is it good? Not good.
That's good.
Better? And we have here, like this, and we said the current goes down, right? Is the current goes down? Here. Right? The current goes down, so the current goes here, right? And the magnetic field goes this way, so that is the direction for the B. the current goes down, but actually we know it's not the positive charge goes down. It is the electrons going up, right? So actually we have some electrons here going up. Does this make sense? We discussed this in the very beginning, right? The current goes this way, then the electrons go up. This one is negative, right? And this V is in this direction. So V is in this direction. So I said V is in this direction. Right? Then QVB, V cross B, use your right hand this way. So that means the force will be in this direction. V cross B is in this direction, right? But there's this force, this here is negative. So it gives us directions inside. That means this one here will curve to inside. So this one move this direction at the same time goes inside because it suffers a Lorentz force which is inside. So this one will go like this. Then negative charge go this way, then positive charge will go this way. So we are going to have some positive charges, negative charges on these edges. So now you can see. This positive will be on this edge, negative electrons will be in this edge. Does it make sense? Right? I summarize here. The electrons will go from here to up, and it will suffer an electric force called Lorentz force. Then the force will push the electrons to inside this ball, which will be accumulated on this blue edge. Electrons will be in this edge. Then that means positive will be on this red edge. So this one is positive, and this one will be negative. So that gives us the pole voltage. Okay? I suggest you download this PPT, then you play on your computer, you can see it. Right? Any questions? Right? Good? Solenoid is like this, a coil and magnetic field, and there's a spring here. So this can be used as a mechanic switch. It's an electrical mechanic switch. And this has a lot of applications. For example, the automatic automatic switch like this one, right? To control the fluid in the pipe. We just apply electric signal current. If we have electric current applied to this coil, then this coil will give us a magnetic field. Okay? This magnetic field will push this part either closed or open. So this one can do like this. So we use electric signals to control the mechanical motion. If we use this kind of device, this one is a relay. A relay is an electrically controlled switch. You can see like this. How this works. This is a diagram. This one is called normally. This one is NO. You need to read the textbook, right? This code is NO. Means what? Normally open. This one is called NC. This means normally closed. If we don't have this switch is always like this. Right? Always closed to here, NC, always open to here, NO. But if you apply a voltage or current here, this current flows through this coil, we are going to have a generated magnetic field. Right? This magnetic field will turn this one to this way.
Yeah.
So this one will close this one. If you disconnect this current, then it will go back. So use this one. So we can use electric signal to control this magnetic switch. Right? So this is very, very neat. And the physical structure looks like on the left. This one is the diagram. If you draw, like for example, if later time you are going to be engineers or technologists, you need to draw. For some buildings, you need to draw the diagrams. You do not draw this. Instead, you draw something like this. And also the resistors, you do not draw the actual resistor, right? You draw like this thing. So that, you need to be able to read this diagram and draw the diagram by yourself. Alright, so this one is here, another schematic symbol for electrical switch. No C. What is no C? What is NC? No, normally closed. NO, normally open. So you can see. Alright. We discussed the magnetic field flux before. Now there's another quantity, it's called magnetic field intensity. What is intensity? Intensity is something like the strength per unit, right? It's like a strength. So magnetic field intensity is the magnetic force per unit length of a magnetic path. And we use H to represent this magnetic field intensity. So it will be equals the mmF then per unit length and divided by length. The Fm is the current multiplied by the number of turns. So again, H equals Ni divided by the length of the magnetic path. So all these numbers right here. Magnetic field intensity, don't be confused with the magnetic flux. Magnetic flux density. This is called magnetic field intensity. So you see the difference. Represents the effect that a given current must put into establish a certain flux density in the material. One more time, right? Yeah. Okay. A material is permeable, then a greater flux density will occur for a given magnetic field intensity. The relationship between B, which is flux density, and the H will be B equals mu times H. B equals mu times H. So if the material is permeable, that means mu is large. Then for a smaller, the H, we are going to have a larger magnetic flux density. H is the magnetic field intensity. Okay. Again, all these units are standard units. But it looks like this relationship is linear, right? The larger the H, the larger the B. But this is not always true. If the magnet is saturated, then no matter how you increase the H, the B will not increase. Right? So that is called magnetic saturation. The slide here does not discuss many details. But at the end, there are some exercise questions that they discuss. They use a lot of details. So you need to read their textbook. Remember this one, look at it on top, summary. Right? We do not discuss everything in the textbook, but you need to read the textbook. Alright, relative motion. When a wire is moved across magnetic field, we have a relative motion. Relative motion means the motion is relative, right? So if you stand still, I move, we have a relative motion. If I still, then you move, we have. So no matter the wire moves or the magnetic field moves, both we have relative motion. So what happens if we have a relative motion? Like this one. So we have a magnet here, N and S. This is fixed, does not change. Now we have this wire move from the right hand side to the left hand side. Look at this again. This is called relative motion. Or when the magnetic field is moved past the stationary wire, then it's also relative motion, like this. The wire does not move, but the magnetic field moves. So we also have relative motion. So in either case, the relative motion results in induced voltage in the wire. That is the thing you are discussing about the wireless charging. So we are going to have an induced voltage. That induced voltage will charge your device. Again, we cannot discuss a lot of details. You may know more details of this in physics and also in higher level. So, for example, electrical power, we discuss motors, generators, electromagnetic, we are going to discuss. If you have interest, we are going to discuss more details of this. So we just cannot give you a lot of in this class, this introduction. The induced voltage is proportional to the magnetic field and also proportional to the length of the wire and also is proportional to the relative motion speed. So that V, the first V is the induced voltage equals B times L times V. V. The V is the speed. If you move faster, then the induced voltage will be higher. Alright, now let's we may don't do this lab experiment in the lab. You may do this in the physics class. So Faraday's law. So like this, we have a coil. We connect this coil both terminals to the two terminals of the voltmeter. What do you expect? What do you expect here? Nothing, right? Just a straight wire, just a wire coil with nothing. Right? Now, if we have a magnet like this, move inside or just anywhere like this one, we have a relative motion. What do you expect? We are going to have, yes, so when this one will move, that means we have a detected voltage. That is called the induced electric voltage.
I've done this before. That's the thing where, like, if you drop it through it, it'll actually slow down.
Yes, okay.
It's almost like anti-gravity looking thing. It's like the object will just physically slow down even though it's not touching anything going through it because it produces the current going through the wire.
If you have like a copper pipe, right?
Yeah.
You put something, copper pipe like this long, you put something inside, it's not like drop to the ground as fast as it should be. Just very, very slow.
It's just like in midair.
And at the same time, if you do this a lot of times, you feel the pipe will more. So the energy, right? So that is.
It's really cool to see. Like it really is. Like you need to look that up on YouTube.
Right? So if we have a magnet pass through this, then this one will, the needle will change. That means we have induced voltage. Again, if you like videos, you go to the website. There are a lot of videos of this called Faraday's law or Faraday's effect. Faraday's voltage, no matter what, you can check. Yeah, like that. Look at the needle. Right?
Like the slideshow can't it's really.
And if we have a coil carrying electric voltage current, then we are going to have a magnet generating. That is called an electrical magnet. Again, there are a lot of applications. For example, we have a bunch of metal cracks. So we suppose to have some like image here. If you have very large disk, you apply the voltage, the current, then it is a magnet. Yeah? You put on the scraps, then you can hold this. You move somewhere to your destination, then you cut off the current, then the magnet is gone. Then everything is dropped on the ground. So that is electromagnet. Alright, this one is the DC generator. Anyone knows who has an electric generator at home? Right? Oh, a lot of you have this. Right? The basic concept is this is the coil here, right? And this magnet inside. Definitely you need to have this. And if you turn this one here, mechanically, what we do is we use the gasoline or something like that. To turn this, then there will be electric current, electric voltage induced at these two terminals. We are going to have electric voltage induced here. If you close these two terminals with like a lamp or any device load, then there will be an electric current can do the work. So this is called the electric generator. The mechanical force or energy is converted into electricity. And also, this need to use the Faraday's induction law. This one is a motor. Motor is more popular right now, right? Because we have electrical car. So what happens in a motor? We have a battery, supply a current to the coil here. So you have this one applies just opposite to the generator. You apply the current to this way, then this one will automatically turn. By some configuration, you need to make this perfect. It's continuous turn. So electric current, electric energy will be converted into mechanical energy. I'll give you another secret. Electric generator and the electric motor are the same thing. You can use an electric generator as a motor. You can use a motor as an electric generator. Depends on what is your input. If you turn that input physically, then you are going to have an electric current. If you have electric current input to that one, then you are going to have next time I'll bring something to show you. That thing is a motor that drives the printer before. But we connect it, then I turn that one, you can see it change into a generator. So next time, hopefully I remember I bring this, let you take a look. Alright, all this unit, I know that it's not easy to memorize all this, but you need to memorize, try to memorize some of it. Right? Magnetic field. Still remember this? Magnetic flux. V is the unit for magnetic flux, right? Permeability. Mu, reluctance. And magnetomotive force. How to calculate this? N times I, right? And solenoid induce the voltage. This is very interesting. Everybody likes this, and there's a lot of applications. Very useful. We are going to learn this more later time. Faraday's law, induction. Okay, now let's do some exercise. The first one. The unit of flux density that is the same as Weber per square meter is what is the unit for magnetic flux density? A. D.
No, it's D.
D, right? It is Weber per square meter, but we call this Tesla, right? Okay, next one. If a magnetic circuit has a larger flux than a second, then the first circuit has the flux and the flux density. We are going to discuss the relationship between flux and the flux density. So how to calculate flux density from a flux? Density means per unit area. So flux divided by the area equals the flux density. So they have one has a larger flux. They discuss the flux density. So which one? C. A lower? Like this one. You travel longer than me, right? Then your speed and my speed, which one is faster? You travel longer distance than me. What's your speed? Speed faster than me or smaller than me? Same?
I don't know. It's about so deep.
D, right?
Yeah.
Depends on the time. You travel 10 miles in 1 year. I travel 1 mile in 1 hour. So obviously I'm much faster than you. This one the same thing here. Right? It divided by the area. So we need to know the area. Right?
1 mile an hour. 1 mile 1 year.
The cause of a magnetic flux is which one? A, right? Magneto-motive force. The measurement of unit for permeability is there's a meter, there's a length on the bottom, so I believe it is C, right? What is the measurement unit for relative permeability? Relative, compared to the mu in free space. Which one? D, right? Unit is. The property of a magnetic material to behave as if it has memory. Yeah, again, we didn't discuss in this slide, but the answer A, yes? A. Remember, okay, that's not.
C.
B. I said that we didn't discuss in this.
Oh, we did discuss
So
this.
which one? We didn't. Which one? That is the trick you guess, right? Educated guess. Oh, I didn't discuss this concept. Which one is A? A. B. Not A.
D.
Not D.
C.
D.
We discussed the C. Okay, so that is the B. Right? B. It is B. You read the textbook. Ohm's law for magnetic circuits is which one? C. Okay, good. The control voltage for relay is applied to
Normally.
Close.
Control voltage for a relay. It's normally.
we have a signal electric current to control the relay. The current is applied to
C, the coil.
the coil, yes. Right? So the coil we are going to generate a magnetic field, so that magnetic field will control this the switch to the right? Okay, this one. Okay, we didn't discuss this, right? That is the answer is B, okay, boy. Right? When the current through a coil changes, the induced voltage across the coil will, we only said there will be induced voltage in this slide, but we didn't see what direction. It is opposite the change in the current that causes it. A, correct. You read the textbook, okay? Okay, that's it for today. Y'all want to go put on there? Hell yeah, let's make it.